Hey, welcome back to another deep dive.
Hello.
Today, we're really getting down to brass tacks, peeling back the layers to the absolute foundation of geometry.
That's right. We're looking at the essential building blocks.
Yeah.
Points, lines, and angles.
And for this, we've basically distilled everything from our source material.
Yeah, think of it as a really focused guide. The source lays out these fundamental concepts very clearly.
So our mission today is pretty straightforward. Pull out those key definitions, the core relationships from this source material.
Exactly. So you can get a solid, quick grasp on the grammar of geometry that explains so much around us.
Okay, let's dive in. Where does the source start? The absolute simplest thing.
Right at the beginning, as you'd expect.
Yeah.
With a point, which is really just about position. No size, nothing else.
Just location.
Okay.
And from points we get
Lines. Infinite length, the source emphasizes, but zero width. Then parts of lines. Line segments, which have two endpoints.
Fixed ends.
Fixed ends, yeah. And rays, which have one endpoint and then just zoom off infinitely in one direction.
And we need somewhere for all this to happen, right?
A plane.
Exactly. A flat surface.
Yeah.
Like a piece of paper that goes on forever. These are the sort of basic ingredients the source gives us.
Right. Okay, so you've got these line segments, rays. What happens when they, meet up? That's angles, isn't it?
That's exactly where angles come in. The source defines an angle as being formed when two line segments or rays share a common endpoint.
That endpoint has a name, right?
It does. It's the vertex. And the two segments are rays. Those are called the arms of the angle.
So it's kind of measuring the opening between them.
Precisely. The turn or the gap between those arms. And the source quickly gets into classifying them.
Yeah. Based on that turn, you've got the small ones, acute, right? Less than 90 degrees.
Then the perfect corner, the right angle, exactly 90 degrees.
Then bigger than that, obtuse.
Yep, between 90 and 180. Then the straight angle, which is just a flat line, 180 degrees.
And the big one, reflex. Right. The reflex angle goes beyond the straight line, so between 180 and 360 degrees. Knowing these types helps you describe things quickly.
Okay, so those are individual angles, but the source doesn't stop there, right? It talks about how they relate to each other.
It does. And this is where it starts getting really practical. It talks about adjacent angles first.
Adjacent meaning next to each other.
Sort of. They have to share the vertex in one arm. They're side-by-side angles.
And that leads to something important. The linear pair?
Yes. A linear pair is a specific type of adjacent angle pair. They sit next to each other, and their non-common arms form a straight line.
Ah, so they add up to 180 degrees.
Always. The source states that very clearly. Their sum is 180. They're supplementary, super useful rule.
Okay, what else? What about when lines just cross each other, like an X?
Good one. That creates vertically opposite angles. Think of that X. Shape the angles directly across from each other at the intersection.
And the source says?
They are always equal. Always. Another incredibly handy fact for figuring out unknown angles.
Makes sense. The source also mentions angles all the way around a single point, right?
It does. They all add up to 360 degrees, a full circle. And also, angles just on one side of a straight line add up to 180.
Right. And then there are those two other key pairs, complementary and supplementary.
Yes. Complementary angles are any two angles whose measures add up to 90 degrees. They don't have to be adjacent.
And supplementary.
Any two angles whose measures add up to 180 degrees. Again, they could be anywhere, not necessarily forming a linear pair.
Okay, so we have angles, types of angles, and how they relate. What's next in the source material's logic? Parallel lines.
Exactly. Now we bring in parallel lines.
Which are lines on the same plane that just never meet.
Correct. They run alongside each other, always the same distance apart, never crossing.
And then the source introduces something that cuts across them. A transversal.
A transversal line, yes. It's just any line that intersects two or more other lines, which are usually parallel in the interesting cases.
And this cutting action, it creates special angle pairs, doesn't it?
Oh, yes.
Yeah.
Whole bunch of them. The source highlights three key types based on where they sit relative to the parallel lines and the transversal.
Okay, like what?
You get alternate interior angles.
Yeah.
They're sort of inside the parallel lines, but on opposite sides of the transversal.
Okay, inside and opposite sides. Got it.
Corresponding angles. They're in the same relative position at each intersection point.
Yeah.
Like top left at one intersection, top left at the other.
I see. Same spot, different intersection. And the last one?
Co-interior angles. These are inside the parallel lines, but on the same side of the transversal.
Inside and same set. Okay. So we have these pairs, alternate interior, corresponding, co-interior. What's the big deal?
Here's the crucial part, the core theorem from the source. if those two lines that the transversal is cutting are parallel.
Only if they're parallel.
Right. Then some amazing things are true. Alternate interior angles are equal.
Equal. Okay.
Corresponding angles are also equal.
Also equal.
And co-interior angles.
Yeah.
They aren't equal, but they are supplementary.
Meaning they add up to 180 degrees.
Exactly. So, alternate interior equal, corresponding equal, co-interior supplementary, if the lines are parallel.
That's powerful if you know lines are parallel. But wait, the source also flips this, right? This is the really useful bit for proving things.
Precisely. This is the huge takeaway. It works the other way, too. These relationships become conditions for parallelism.
So if you don't know if two lines are parallel, but you cut them with a transversal and you measure...
And you find that, say, a pair of alternate interior angles are equal.
Or a pair of corresponding angles are equal.
Or you find a pair of co-interior angles add up to 180. Then you know for sure, based on the source material's theorems, that the original two lines must be parallel. It proves parallelism.
Wow. Okay, that's incredibly useful. It's like a test.
It's a fundamental geometric test. So understanding these basic definitions, the angle types, and especially these relationships with parallel lines, well, that gives you the whole framework.
Yeah, this deep dive really pulled out the essential grammar from the source, you know, the rules that let you figure stuff out.
Absolutely. It helps you make sense of shapes and structures everywhere.
Okay, before we wrap up, here's one last kind of elegant little detail we pulled from the source material for you to think about.
Oh, yeah.
Imagine you have that linear pair, again, two adjacent angles sitting on a straight line, adding up to 180 degrees.
Okay, I got the picture.
Now imagine you draw a line that perfectly cuts the first angle in half, a bisector, and then you draw another line that perfectly cuts the second angle in half. Another bisector.
So two lines, each bisecting one of the adjacent supplementary angles.
Exactly. According to the source, what's the angle between those two bisecting lines?
Ah, I see where you're going. So
A perfect right angle, 90 degrees, every single time.
Isn't that neat? It just falls out from the basic definition. Something as simple as cutting angles in half reveals this hidden perpendicular relationship.
Yeah, it shows that underlying elegance, doesn't it? It's right there in the source material.
It really does. Something to visualize next time you see a straight line split into two angles. There's often more geometry hiding there than you first realize.